All right, and next up, we have Majd from NVIDIA, and he will be giving a presentation, Building NVIDIA GeForce Now Network Infrastructure using open source OVN, OVS, and NVIDIA commodity DPUs. All right.
Hello, everyone. Good morning. So I'll start by introducing myself because I haven't contributed any code, so maybe you don't know me. So my name is Majd. I'm managing the ASIP Square R&D group team at NVIDIA at the Networking Business Unit. My group is responsible for the development of OVS, OVN, OVN Kubernetes, and other things. I previously led the RDMA Linux team at Mellanox. So in this talk, we will be talking about how we built the networking infrastructure of the GeForce Now. What is GeForce Now? How we use open source code, open source projects to build an efficient networking, and how we utilize the NVIDIA DPUs in order to meet all the requirements from GeForce Now. Working. Okay, good. Great, thank you. Starting with GeForce Now. So GeForce Now is a cloud gaming. Basically, what we do is we build the gaming rig, so nobody needs to do so. As you know, games are very demanding. They are considered as killer apps. The newer games you have, you need to upgrade your hardware. So same as all the benefits that we get from cloud, same thing goes here for games. We take care of the gaming rig. We upgrade it all the time. We provide you the best GPUs, best networking, and you just need to choose the game and play it wherever you want. We do support Windows PC, Mac OS, TV, mobile, and a variety of different things. The service is live since February 2020, and we have data centers all around the world to provide the best experience for gamers. Having said that, GeForce Now becomes a killer app for private clouds. GeForce Now has its own requirements from the cloud infrastructure. So one of the most important things is actually performance. Since it's gaming, we need the gaming experience to be very smooth, so performance is a key requirement. Security is also not optional. Gamers can be malicious ones and hack out of the game, so we can't afford that. We need an infrastructure, cloud infrastructure, to be very much secured. And cost is a really key consideration. We also want to build a cloud, a networking infrastructure that is cost effective. So this kind of service will be profitable. If we just have this diagram to give you a sense of the requirements of the performance, so we can see over here that we have a very small amount of time to do all the work, including the gaming engine, encoding, decoding, rendering, sending the frames, audio, like audio, video control over the internet. Everything should be very fast, otherwise the gaming experience will be hurt and people will not use this kind of service. So we have really hard requirements, and we need to come up with a very creative solutions in order to meet those. Over here we have like a high-level block diagram of how the GeForce Now infrastructure looks like. So you can see that we use Open Virtual Switch data path for VMs. We have two types of interfaces. We have SRV and PV. This diagram, first of all, was how it looks like before we introduced all the acceleration and the solutions. Okay, so that's pre-DPU. So over here we can see that we had to use SRV interfaces for the gaming in order to get the best performance. Since we didn't have any technologies that are presented by the DPU, we lacked all the security groups that we could have got from OVS and OVN. So all the security had to be on the switches side. That one thing. One more thing is that the OVN agent, because we didn't have anywhere to run it except the host, was run on the host, and that also becomes a security issue because it relies on the hypervisor's protection. Everything is orchestrated by Kubernetes. Control plane is being done with the OVN. So we have OVN, OVS, Kubernetes managing the whole deal. In the upcoming slides, we will look at the solutions, what kind of hardware, what kind of software, what we did in the past couple of years in order to solve all of these challenges of performance, security, and cost. So first of all is DPU, the NVIDIA Bluefield 2. In the previous talk, Harish explained it very well, so I will not go over it very deeply. But DPU is mainly having a Connectix 6D. Bluefield 2 is mainly Connectix 6DX, which is a smart NIC with many acceleration and capabilities, paired with the 8 ARM cores that are programmable. You can run whatever you want, and the whole thing is isolated, a system on chip that is isolated from the host itself. So the NVIDIA DPUs give us a new trust domain, a new isolation that can benefit us from security point of view, and we can still enjoy all the acceleration that are offered as part of the Connectix silicon. On top of that, we have also much more features such as storage offload, security offload, that we will less talk about them in this meeting, but it's good to know that we can add on top of those capabilities even more accelerations and more offloads. So first technology, and it's one of the main technologies that was used in order to overcome the performance issues and the security issues that were key requirements for the GeForce Now, is the ASAP Square. ASAP Square is the accelerated switching and packet processing. So mainly what we get with ASAP Square is the virtual switch control plane stayed intact. We don't touch the control plane, but yet we enjoy the acceleration of the data plane inside the hardware. And all of this is done with standard hardware abstraction interfaces such as TC or DPDK RTE flow. So mainly ASAP Square is enjoying both worlds. We have the performance of the SROV interfaces, but yet it's programmable in such way that we had with the PV. So ASAP Square really enjoys both the worlds and give us a good answer for the programmability without compromising on the performance. I'll talk briefly about it because I think this topic was discussed many times in the past, but for those who don't know how it works, so we'll touch it in very briefly. So on the left side, we can see how software-only OVS implementations work. First packets go through the kernel data plane. Most likely, they will miss and go to with the upcall to the user space daemon. Over there, we will parse the packet, understand which kind of actions matches needs to be done and to which port it needs to be transmitted. This kind of info is then sent back to the kernel data plane. The packet sent back to the kernel and being handled by the kernel. Subsequent packets that will have a hit on the kernel databases will handle faster in comparison to going all the way to the user space, but it's still not as fast as in the hardware. In the right side, what we can see is the solution, how ASAP Square actually works. It's worth to mention that in order to enable ASAP Square with OVS, we had to do changes to the OVS code, kernel code, and all of this code is upstream years ago. So the way it works with ASAP Square, first packet, same as before, will go, first of all, they will go through the NIC, obviously. The first miss will happen in the NIC. They will go all the way to the kernel. Kernel will miss as well. They will go with the upcall to the user space. In the user space, we will know what to do with this packet. This kind of info is propagated back to the kernel, up to the kernel drivers that are responsible to configure the embedded switch that is inside the smart NIC. In the kernel driver, we understand which kind of matches and actions are requested by the upper layers. We build the desired hardware model, and configure the hardware accordingly. And then what happens is that the subsequent packets, instead of hitting a miss in the hardware, in the embedded switch in the hardware, they will know what kind of actions and matches needs to be done and to which port it should be transmitted. So all the packets will merely go through the hardware and will be transmitted to its final destination via SRV to the desired pod or VM that needs this data. So we can see that once everything is offloaded after this kind of learning stage, all the traffic will be fully offloaded in the hardware. Neither the kernel or the user space will take any part of the data plane, and the data plane will be much more accelerated and freeing a lot of CPUs. Some of the capabilities that we have with embedded switch that A-subscript technology can utilize. So we can see over here a big list of the things that we can do. It's worth to mention that these are like the hardware building blocks, and for each controller or each application that we want to accelerate, we can take these building blocks and build the hardware model, whether it's in the DPDK application or kernel application. So we can do a recirculation between tables. We can do any matches and actions that you can think of, matching on IPv4, IPv6 header, TCP, UDP, inner packets, outer packets. We can support a variety of different encapsulations. We can do many different actions, allow drop, rewrite, hairpinning, sampling, countering. So the hardware is capable of doing all of those, and it's a matter of the software that is on top. In this case, it's the kernel driver, the Manus kernel drivers, to get the request from upper layers, which is TC in our case, and build the hardware model according to these building blocks to mimic whatever is being done in the software to be identical in the hardware. And this way, we can enjoy the same data plane in the hardware, but in a much faster way. Now jumping to the OVN SDN acceleration itself. So over here, what I wanted to emphasize is the work that we had to do in the past maybe couple of years, a bit more, in order to get the whole OVN Kubernetes offloaded inside of our hardware. So as I previously explained, hardware offload is something that we need to do per feature. It's not something like once we put OVN on top of DPU, everything will be magically accelerated. We need to add the features. So the work that we had to do over here is really examining which kind of data path flows are being generated by OVN and OVN Kubernetes, analyzing what are the gaps from feature set point of view, implementing all of those inside of our kernel drivers, and eventually we ended up having all the OVN Kubernetes flows fully offloaded. This kind of work really required a lot of features to be added. We added support for connection tracking, which was one of the biggest part, and we had a collaboration with many different members in the community to get this big technology inside. We had to add support for Geneve encapsulation, decapsulation, because as you may know, OVN Kubernetes uses Geneve tunnels, or OVN in general uses Geneve tunnels for all the east-west traffic. Support for netting, support for hairpinning, for different use cases. So the list of the features that we had to implement inside of our kernel drivers and integrate with the upper layers was huge. And end of day, we ended up with a fully offloaded data plane for almost all the relevant Kubernetes flows. We support, I guess, around, at least tested, even, I think we support more, but at least we tested around 32 different common Kubernetes flows, and all of them are fully offloaded, meaning all the data plane is being handled merely in the hardware without any CPU doing any data plane actions. Also, as you can see, one more benefit of the DPU is that we could eventually offload all the control plane inside the ARM cores. So over here we have basically two benefits. One, that all the obvious data plane is accelerated and offloaded inside the ASIC. So this way we achieve a better performance. And second thing is the offload of the control plane into the ARM cores, which provide us a much better security. Offload the x86 cores and freeze x86 cores, and this way we have a more cores for the actual tenant work. And it's more isolated and secure this way because the host can't really access anything inside the ARM cores. Now, if we put all these technologies together and look again at the block diagram and see how we can benefit from those. So today, instead of the commodity NICs that we had previously, we have DPUs. The DPUs allows us to have a programmable SRIV. So a gaming that previously had SRIV but was not managed by OVN is now managed by OVN. This way we can enjoy all the security groups and have enhanced security even there and avoid doing that directly on the switches, on the physical switches. We put all the OVN control plane inside the DPU, and this way we have a better isolation and enhanced security. And the fact that we save CPUs that were previously used by the data plane and the control plane is reducing also the cost, which was a key requirement. Just to give you some sense of the performance benefits and the CPU utilization. So what we did here is we wanted to compare PV to ASAP square. So on the right side, we have a connected 6LX, but without any hardware offload enabled. So it's just like a commodity NIC with the PV interfaces. And in the left side, we have Bluefield 2 with OVN. With OVS running on the Bluefield 2 with ASAP square technology enabled. And the motivation of this comparison is to show comparing the performance that we can get with a non-accelerated solution and how many cores we can save. And one more thing, it's like the usual thing. We generate the traffic using Xia. We send it all the way to the VM. The VM runs some DPDK application like TestPMD or whatever, sends the packets back, and this way we can measure the bandwidth, packet rate, and so on. As you can see, in the left side is the non-accelerated solution with the PV interfaces. In the right side, we have the ASAP square solution with the SRV programmable interfaces. In the left side, we can see that with 5K connections running traffic of Geneva with connection tracking and NAT, which resembles what is actually happening with OVN, we had a limit of performance around 17 gig, and we had to use 19 cores just to reach that on the host side. We couldn't reach any more bandwidth. We tried to change the RSS and utilize more cores, but we saw that the limit was on 19 cores. So 19 cores were only capable of giving 17 gig out of the 50 gig that we could get. And as we understand, like it's a large amount of cores. On the other hand, when we look at the Bluefield side, so we could reach a line rate of 50 gig without any cores because we save all of those cores, data plane and control plane, by accelerating to the ASIC or offloading to the ARM. And same kind of flows can have a line rate with 0 cores. So the benefit is huge. We can reduce 19 cores and more than double the performance. If you look at a larger scale test where we have 500,000 connections in the same kind of setup, so we saw that the limit of the cores was with 32 cores. Any more cores didn't help, and the performance drastically dropped to around 8 gig. And on the other hand, Bluefield accelerated solution maintained the same line rate with this big amount of connections and saved all these cores. To summarize, so as you remember, we had 3 key requirements: security, cost, and performance. So first of all, we can see that we have enhanced the security by isolating all the control plane into the DPU ARM cores. So this kind of offload provides us a better security because even if the malicious users can have access to the host, they will not be able to touch anything that is related to the control plane that is running on the ARM cores. We can see that we have enhanced the performance on top of the SRV interfaces thanks to the ASAP square without harming the performance. We saw previously that we can really sustain a line rate of 50 gig very easily. So this way we still use, in this sophisticated case where previously we had SRV already, so we had a very high performance for the gaming interfaces. the requirement was really preserving the same performance, but adding additional security, and we could achieve that really thanks to the A²² technology. Cost is really reduced by saving all these CPU cores and power consumption that is the power that the CPUs are consuming. So we could see in the previous slides that it can get up to really 30 CPUs that can be saved in this way. So cost is drastically reduced, and power consumption as well. Data path acceleration is achieved also to the PV interfaces that were moved to become SRV. So right now in the GeForce Now infrastructure, everything runs on SRV interfaces, and all of them can enjoy even a better performance for data plane. All code is open source. All what I have described is part of the open source different communities. We have all the code in the kernel upstream. We have the code in OVS, OVN, OVN Kubernetes. All the work that we did for the DPU mod is also upstream. So this kind of technology is really commodity. Everybody can use it, and it will be available in the upcoming distribution by different vendors and can be used out of box. And worth to mention that this is just the first phase of accelerating stuff, and on top of that, we will be able to add even more and more acceleration for storage, for enhanced security, for example, encryption, decryption, on top of the same architecture. Thank you. That's all. Questions?
We got time for one or two questions.
Okay. Hi. I have a very simple question. I noticed you mentioned that the source will be released and stuff, but is this actually live currently for people who are subscribed to GeForce Now?
Yes, it is live on certain data centers. So yeah, this technology is already in production. It's not just nice slides, but yeah, it's actually working.
Okay, thank you.
So you said on the Bluefield 2, there are 4 cores that are being used, right? Like, what are those cores being used for?
You mean in the diagram?
Yeah.
No, so it's not on the Bluefield. These cores are on the host.
Host, yeah, but...
So these are the ones that are used by the test PMD to send the traffic back.
Okay.
So the VM, maybe I didn't mention it here, but the VM has 4 cores that are being used in order to steer the traffic and send it back to the traffic generator.
Those are just test PMD cores.
Mm-hmm. Right.
All right, and we have one online question.
All right, so James is asking, I get the arguments for of security and freeing up CPU cores for OVS, OVN offload to a DPU, but aren't there going to be scenarios where the weaker per core performance of DPU impacts OVN/OVS?
A good question. So maybe in theory it can, because as you know, ARM cores are weaker. What is worth to mention here that when we are comparing the work, then the work is also different. All the data plane in case of A² is fully offloaded, so we don't need the same amount of cores compared to the non-offloaded, non-accelerated kind of work. So the work that OVN and OVS needs to do in the accelerated and the offloaded case compared to the non-accelerated case is less. So we can live with a weaker cores. From our experience, we haven't met any issues yet with the scale that we are using due to the weaker ARM cores. But it's also worth to mention that in the newer generations of Bluefield, for example, Bluefield 3 will have double the amount of cores with a much stronger ones. So control plane things will enjoy a better cores, and hopefully there will be no issues for scaling, big scale or performance related to that.
All right, thank you very much. One more round of applause for Majd.
Thank you.